Alright, so in this video we're going to talk about the acceleration due to gravity g. So we've been using the value of g to be as 9.8 meters per second square on the surface of the Earth. We have always more or less accepted that as an experimental fact. In fact, there are many simple experiments that you can do to measure the value of g, and you'll find that it's approximately 9.8 meters per second square. Where does this little g come from, and why does every object on the Earth have the same, any object that's freely falling near the surface of the Earth, why does it have the same acceleration of 9.8 meters per second square? So we can understand that now in a little more depth from Newton's law of gravity. So we know that the weight of an object is the force of gravity on that object. That's the definition of weight. So suppose you've got an object, suppose you've got the Earth like this, and you've got an object of mass little m. Let the mass of the Earth be capital M, and the object, the small object, is at a height h above the surface of the Earth. Let me draw the radius of the Earth here. Okay, I'm going to call r the radius of the Earth. So let's calculate the force of gravity on this object. Right? So based on what we've learned in this chapter, you can use the shell theorem and treat the Earth as a point mass located at its center. So Fg is going to be equal to gm little m divided by the distance between the object and the center of the Earth. So that's r plus h squared, and that is going to be the force of gravity. Right? Now, what did we use for the formula for weight up till this chapter from the beginning of the course? So we used m times little g, right? So we can set these two equal, and immediately we get an expression for g. So g is equal to g capital M divided by r plus h squared, where r is the radius of the planet, Earth in this case, and h is the height of the object above the surface of the Earth, right? And so this is the accurate expression for g. You can see that g is not strictly constant, but it depends on the height above the surface. Now, suppose we are talking about normal heights, like an object being dropped from the top of a building or something like that, like all the cases that we've looked at so far. So what is the radius of the Earth? The radius of the Earth is 6,400 kilometers, and most of average heights, like the height from the top of a building, the height of a hill or stuff like that, all of that is very, very small in comparison to 6,400 kilometers. Even Mount Everest, the height of Mount Everest is 9 kilometers. So that's very, very tiny in comparison to the radius of the Earth. H is much less than r for objects close to the surface of the Earth. So you can ignore the h, and so you get this approximate but fairly accurate value of g, which is gm divided by r squared. I'm ignoring the h. So if you plug in g equals 6.67 times 10 to the negative 11 Newton meter square over kg square, mass of the Earth 6 times 10 to the power of 24 kgs. It's actually 5.97, but I'm just putting down 6 times 10 to the power of 24 kgs. And radius of the Earth, which is 6.4 times 10 to the power of 6 meters. If you plug these three numbers in, and you can do it yourself, you will get, what do you think you'll get? You'll get g is 9.8 meters per second square. And that is where the 9.8 meters per second square comes from. So from this formula, that g is equal to gm divided by r squared on the surface, you can calculate the value of acceleration due to gravity for the moon, you can calculate it for the sun, you can calculate it for any planet for which any object for which you know the mass and the radius. So that is where the 9.8 comes from, in the acceleration due to gravity. And you can also understand why the acceleration due to gravity is not constant. All right. On the other hand, when h is large, so if you're talking about a height which is comparable to the radius of the Earth, then g is certainly not a constant at all. So remember that the correct formula is, the accurate formula is g is equal to gm divided by r plus h square. So when h is not incredibly tiny, like if you're talking about an object that's being a rocket that's being sent to space, and the rocket, let's say, is at a height of half of the radius of the Earth, a few thousand kilometers, then you cannot assume that g is fixed at 9.8 meters per second square. So g is 9.8 meters per second square only near the surface of the Earth. All right. Let's look at an interesting application of our formula, of this formula. G is equal to gm divided by r square. So that is the problem on slide 13 concerning the neutron star. How much would a person, a 100 kg person, weigh on the surface of a neutron star? And you're given the mass of the neutron star. The mass of the neutron star is 2 times 10 to the power of 30 kgs. And you're given the radius of the neutron star. Now, 2 times 10 to the power of 30 kgs is an enormous, enormous mass. It's actually the mass of the sun, and it's sometimes written like this. That this symbol in astronomy just means the mass of the sun. Radius of the neutron star, and compare that with the mass of the Earth. Its mass of the Earth is only 10 to the power of 24 kgs. So that's like 1,000,000 times the mass of the Earth is what we're talking about here for the neutron star. What about the radius of the neutron star? The radius is only 15 kilometers. And you did not read that wrong. It really is 15 kilometers, or about 9 miles. So you can imagine how incredibly, incredibly, incredibly compact this object is, a neutron star. Just unbelievably compact. Its mass is the mass of the sun, and its radius is about the size of a city block. It's an extremely, extremely compact object, right? You can calculate the density of a neutron star. The density will come to something like 10 to the power of 17 kgs per meter cubed. What was the density of iron, lead? These things have densities of a few thousand kgs per meter cubed, right? We are talking about 10 to the power of 17 kgs per meter cubed. This is an absolutely unbelievable density. So to give you an idea of how dense that is, if you take, there are many analogies which are often used to convey what this density is like. So if you take all the human beings on planet Earth, like all 6 billion human beings, and if you squeeze them to a size of a sugar cube, right, the density that you're going to get is the density of a neutron star. Then you get this 10 to the power of 17 kgs per meter cubed. Another analogy is if you have a tennis ball and it's made of neutron star material. So just imagine taking a tennis ball's worth of neutron star material, and how much would that weigh? You can easily calculate that it's going to weigh about 20 trillion kgs. So a tennis ball worth of neutron star material is going to weigh 20 trillion kgs, which is about 40 times the estimated weight of the entire human population. Just a small teaspoon of neutron star material would weigh something like Mount Everest. So neutron stars are extremely dense, right? So anyway, so you can, if you plug in these numbers into G, the formula for G, you can get the value of G near the surface of the Earth. Near the surface of a neutron star. And then you can do mg to calculate the weight of the person near the neutron star, and that would come to 6 times 10 to the power of 13 newtons. That would that would be the weight of a person near the surface of a neutron star. What would happen to the person if they did approach the surface of the neutron star? Well, what would happen is this force would cause the person to shrink down to the size of to the thickness of a sheet of paper. Uh, all right. Okay. So neutron stars are really bizarre and amazing objects, and uh, they also produce incredibly powerful magnetic fields, extremely powerful magnetic fields. And if a neutron star were to approach within 100,000 miles of the Earth, uh, then the magnetic field of a neutron star would be more than enough to wipe out every credit card on the Earth's surface. Anything that has that stores information magnetically, every credit card, every hard disk would be wiped out if a neutron star were to approach close to the Earth's surface, close to the Earth. So neutron stars are very strange, bizarre objects, and on I have a little hyperlink on that problem, and if you're interested, you can read a little more about neutron stars over there. Okay, so that's our discussion of G, and now you know where G comes from, the value of 9.8 on the Earth's surface, and you know that G also depends on height, and you also know how to calculate G for any other planet or moon. All right, so the next thing that we're going to talk about is gravitational potential energy. Now, you might be thinking that we already know what gravitational potential energy is. The formula that we had for gravitational potential energy earlier was that if an object is at a height h, then the gravitational potential energy of the object was mgh. So you might be wondering, why are we talking about gravitational potential energy now? Well, the formula mgh is only approximately true near the surface of the Earth because it is derived under the assumption that G is constant. So U equals mgh is only true near the surface of the Earth. And it's based on the assumption that G is approximately constant. However, if we are interested in the gravitational potential energy of something that is at a great height, so something that is at a height which is comparable to the radius of the Earth, then little g cannot be treated as a constant at all, and so you have to get a more accurate formula for gravitational potential energy. Um, so let's go ahead and do that. So to find the formula for gravitational potential energy, you would just start with the equation for the definition of potential energy, which is the change of potential energy, the difference of potential energy is negative of the work done by the conservative force, which is gravity in this case, right? This is how we derived U equals mgh. If you go back to the chapter 6 and 7 lectures, we can follow the exact same procedure to get a more accurate formula for gravitational potential energy. Instead of using the fact that the weight of the object is constant at mg, we just need to put in the fact that the weight of the object is given by Newton's law of gravity, which is not fixed, which depends on distance. So if you do that and do a few lines of calculus, you can get a more accurate formula for gravitational potential energy. So I'm skipping the derivation of that just because those of you that take physics 2 will see something very similar when we talk about electrostatics. And at that time I do the full derivation, so I don't feel too bad about skipping the derivation now. So, but if you're interested in the derivation, you can just check your textbook. It's very simple, just a couple of lines of calculus to get to the answer. So, okay, so let me just write down the formula for gravitational potential energy. Suppose you've got two masses m1 and m2, and the distance between them is r. Then the gravitational potential energy of these two masses is going to be g negative g m1 m2 divided by the distance between them. So two things to remember here are the negative sign, which I personally always forget, and the formula, the denominator has an r and not an r square, right? So that is the formula for gravitational potential energy. Okay, where is the gravitational potential energy zero according to this formula? So we'll call this the accurate formula for gravitational potential energy, whereas mgh is just an approximate formula. Where is the gravitational potential energy zero? So, or in other words, suppose I have a mass, suppose I have the Earth with mass capital M. Where can I place a mass little m such that its potential energy, gravitational potential energy, would be zero, right? Now, when we were working with MGH, you could choose the zero of potential energy wherever you wanted. So we would usually choose that to be the ground, would be our H equals zero. But notice that you don't have that freedom in this formula. This formula has the zero of potential energy already built into it, right? So where is U going to be equal to zero? Clearly, when R is infinity. So U is equal to zero. The zero of potential energy is already built into this formula at R as R tends to infinity, right? Okay, and notice that U is always negative. That's generally a fact. Whenever a force is attractive, potential energy is usually negative. All right, so this is our formula for gravitational potential energy. One other thing I want to point out, what is the gravitational potential energy of an object that's sitting on the Earth's surface? Now, you might again be tempted to say zero, because that's what we've always done when we work with MGH. We would just choose potential energy on the ground to be zero. But can you say that the potential energy is going to be zero if an object, for an object that's sitting on the Earth's surface? Let's think about that. So suppose our mass m here is on the surface of the Earth right here. The radius of the Earth is r. So what is the gravitational potential energy going to be? Now, from the shell theorem, you can treat the Earth again as a point mass located at its center. So if you treat the Earth as a point mass, little m is another point mass, then the gravitational potential energy between them, mutual gravitational potential energy, would be U is equal to minus gm little m divided by r, where r is the radius of the Earth. So the gravitational potential energy of an object that's on the Earth's surface, according to this new formula, is not zero. It's minus gmm divided by r. So please keep that in mind, because that's often relevant in doing problems. Okay, now one other thing is, suppose you've got, we know how to find the gravitational potential energy of 2-point masses, m1 and m2. Suppose you've got 3-point masses. How do you find the gravitational potential energy of all three? Well, you just work in pairs. You can find the gravitational potential energy of 1 and 2 using the formula minus g m1 m2 divided by the distance between 1 and 2, and just so it's easy to refer to them, I'm going to call this distance r12, and let's call this distance r23, and let's call this distance r13. So then you would find u23 same way. I'll just write it down, m2 m3 divided by the distance between them, r23. You would find u31, and then you would just add them up to get the total potential energy. I might as well finish writing this, minus gm3m1 divided by r31. Then you would just add them up to get the total potential energy of the three-particle system. Okay, now let's do an example of applying this So let's look at the example on slide 15. It says that assume that it's possible to fire a shell into space. Find the muzzle speed needed to shoot it up to a height above the Earth's surface equal to the Earth's radius. And it's so what we're doing in this problem is that we have a shell, we have the Earth, right? And we are firing a shell directly outwards. So the shell will travel radially outwards. And the question is asking what speed do we need to fire it so that it gets to a distance which is uh, equal to the Earth's radius. So this is the Earth's radius r. The shell is going up by a distance equal to that. Okay, now you might think that your first instinct again might be to treat this as a kinematics problem, because we've done kinematics problems like this. Like when we first started talking about kinematics, we would talk about what speed. We did this problem where what speed do you shoot something at for it to get to a certain height. So you might be tempted to use the kinematic equations, but can you think about why we cannot use kinematics in this case? Feel free to pause the video and try to come up with the reason why kinematics is not appropriate to use in this situation. The answer is kinematics is only applicable when the forces are constant, right? The gravitational force can be taken to be approximately constant near the surface of the Earth, where g can be taken to be approximately constant. But here we are talking about an enormous height, a height of 6,400 kilometers. So over such an enormous height, the gravitational force is certainly not constant, because the force falls off as 1 over r squared, and so it's not appropriate to use kinematics. However, there is another tool that we can use which is extremely powerful and which is always true, and that is the law of conservation of energy, right? So in physics, you'll find that there are certain tools like Newton's second law, which only works for certain problems. But then when you go to extremes like the very, very small or things moving really fast, then Newton's second law is not useful anymore, and you have to use more sophisticated techniques. However, the conservation laws, principles that we learned, like the conservation of energy, the conservation of momentum, and the conservation of angular momentum, these are the fundamental laws of nature. So these are always valid, regardless of how complicated your situation is. Right? So we can feel free to use conservation of energy in this case. K0 plus U0. We are ignoring friction, so there is no W other, is equal to K final plus U final, right? So let's say that the shell is launched with a velocity V initial. So half mv initial square would be our initial kinetic energy. What is the initial potential energy of the shell when it was on the Earth's surface? The answer is it's going to be minus gm little m divided by r being the radius of the Earth. Notice that I have to use the accurate formula for gravitational potential energy. I simply cannot use mgh, because again mgh is based on the assumption that g is approximately constant, little g is approximately constant. That assumption is not true over a height which is equal to the radius of the Earth. So I have to use the more accurate formula for gravitational potential energy. All right, so then the final point is when it gets to the height that we are interested in, which is r above the surface, and the problem says that it comes to a stop at that height. So what is its kinetic energy? Its kinetic energy is going to be 0. And what is its potential energy going to be at that height? It's going to be minus gm little m divided by 2r. And so from this, you can solve for the initial velocity. And you can just finish the algebra yourself. You can just solve for v initial from here, right? The second part of this problem is very similar. So I'll just let you look at that yourself. Okay. All right, there's an interesting application that one can do from from this. You can calculate the escape velocity of an object from the surface of of any planet or moon or star. So we're going to calculate the escape. Let's just calculate the escape velocity of an object from the surface of the Earth. So first of all, what does escape velocity mean? It means the velocity with which you launch something such that it will just leave the gravitational, it will just fly off to infinity. So it will no longer come back, right? That is called escape velocity. Now, if you take an object and throw it upwards, you know that it's going to keep slowing down, decelerating. It will come to a stop at some point and turn around and come back. The question is it possible to launch something with a velocity that's so high that the object never turns around and comes back? That velocity is called the minimum such velocity is called the escape velocity for that particular planet, right? So how would we calculate the escape velocity? We can actually do it very simply based on what we just learned. So suppose I launch an object from the surface of the Earth, right, with some velocity v escape. So I'll just call that ve. What happens to this object? It just flies off to infinity. It never comes back, right? So when it gets to infinity, an infinite distance away, let's say that we've just given it enough velocity in the beginning to go to infinity and just stop, right? So when it gets to an infinite distance away, its velocity is zero, right? That's really all that we need in order to calculate the escape velocity. So let's set up conservation of energy, and we're going to ignore friction and all that. So K initial plus U initial is equal to K final plus U final. The initial kinetic energy is 1/2 m v escape squared. What is the initial potential energy? It's minus gm little m divided by r is the radius of the Earth or planet that you're looking at, minus gmm divided by r. What then when it gets to the final point, which is an infinite distance away, we are assuming that it just has zero velocity when it gets over there, right? So its final kinetic energy is zero. What about its final potential energy? We know that at infinity, when r is infinite, 1 over r tends to 0. So its final potential energy is also 0. So you have an expression which you can solve, which you can rearrange and isolate the escape velocity. So let's go ahead and do that. If you just do a little bit of algebra, you'll find that v escape squared is equal to 2gm divided by r. And so the escape velocity is equal to 2gm divided by r. And that's the escape velocity. What is the value of the escape velocity for the Earth? If you plug in the value of g, and if you plug in the mass of the Earth and the radius of the Earth, you will find that the escape velocity for the Earth is something like 11.2 kilometers per second. So that's a very, very high speed. So 11,200 meters per second, that's approximately 22,500 or something like that miles per hour. So that is the speed at which you need to launch something in order for it to escape the Earth's gravity. So any spacecraft that leaves the Earth and visits other planets at some point has to get to the escape velocity, right? All right, so that is escape velocity. Now, I might have mentioned one thing, that the Earth has an atmosphere, right? And I might have pointed out that at first it might seem strange that the Earth has an atmosphere, because why don't the gases of the atmosphere just escape out into space? Like, what makes them stick to the Earth? The answer is it's gravity, right? Now, if you look at the average velocity of a molecule of gas, like of a nitrogen molecule or an oxygen molecule, you might have learned the formula for calculating the average velocity of a molecule of a gas in some chemistry class or something like that. If you calculate the average velocity of a molecule, it will come to something like 5 to 6 kilometers per second, which is very fast, but it's much smaller than 11 kilometers per second, the escape velocity of the Earth. As a result of that, oxygen and nitrogen are not able to escape the Earth's surface, and we have an atmosphere made up of oxygen and nitrogen. However, a light gas like hydrogen or helium will not stick around in the Earth's gravity because its escape velocity can be quite high and it can easily escape the Earth's surface. So that's why our atmosphere doesn't have any hydrogen or helium. Atmospheres of uh, much more massive planets like Jupiter and Saturn have an enormous amount of hydrogen because they are massive enough that their gravity, that their escape velocity is way higher and can hold on, and so hydrogen is not able to escape from their atmospheres. All right, so that is the escape velocity. Okay, now on slide 17, I have a list of escape velocities of different um, planets and moons. So, for example, Jupiter has an escape velocity of 50 or almost 60 kilometers per second. The Sun has an escape velocity of 618 kilometers per second. So, it's very, very difficult to escape the gravitational attraction of the Sun. And that is why we have the whole solar system, like all of these planets and then asteroids and comets. Uh, all of these are stuck in the Sun's gravity. They are not strong enough to escape. They're not moving fast enough to escape the Sun's gravity. The escape velocity for neutron star is very close to the speed of light. The speed of light is 3 times 10 to the power 5 kilometers per second. The escape velocity for a neutron star is 2 times 10 to the power of 5 2 times 10 to the power of 5 kilometers per second. So it's just a little less than the speed of light. And the escape velocity for a black hole would be the speed of light. However, um, for a black hole, it is a lot more complicated. Okay, so I probably shouldn't get into all that. So I'm going to keep on talking about this forever. The next thing that we're going to talk about is satellite motion. So think about what we learned when we discussed projectile motion. I think I asked this question in class. Suppose two objects are launched. One of them is thrown horizontally. So maybe this object, this ball, is thrown horizontally, and this ball is just allowed to drop. Right? Which of these is going to hit the ground first? So think about this and see if you can answer this question. So the ball on the left is just allowed to drop, and simultaneously the ball on the right is given a horizontal velocity, purely horizontal velocity, and we are ignoring friction and all that. So which of these is going to reach the ground first? The correct answer is that they would both reach the ground first. And for that, you can take a look at the PowerPoint on projectile motion, where there's a time-lapse photograph of two balls being of this experiment being done with two balls, and you'll see that the vertical motion of the balls is identical. So the first ball, the one on the left, just vertically falls. The second ball falls in exactly the same way, but keeps moving horizontally and ends up describing a parabolic path. So the point is that both of these will reach the ground at the same time. Suppose you increase the velocity of the horizontally projected ball. What's going to happen then? Will the outcome be different? The outcome will not be different. This ball having a higher horizontal velocity will just end up covering a greater, longer path, but it will reach the ground in exactly the same amount of time. What if you increase its velocity even more? Same thing. It will just reach the ground further, but it will take exactly the same amount of time to reach the ground. because its downward acceleration is the same as the downward acceleration of the ball that's dropped. All right, what if I increase the velocity even more? Okay, so um, if I keep on increasing the horizontal velocity, a new thing will start happening just because the Earth is not infinitely flat, contrary to what a lot of people seem to believe. The Earth is actually curved, and so if I increase the horizontal velocity even further, then there will be a point when the curvature of the Earth will start to play a role, and the ball will have to travel a little bit longer in order to hit the ground just because the Earth is curved underneath it while it was moving horizontally. So, in that case, it will take a little bit longer to hit the ground, right? Now, on the PowerPoint, there is a nice animation which unfortunately doesn't play on my iPad. So I can't show it to you right now. I usually show this in class and it's a lot of fun. So I would recommend that you play with this animation a little bit. You might have to try a couple of different browsers to see which one it works on. But basically, here's what happens in that animation. Suppose I launch an object from a certain height with a velocity of maybe 2 kilometers per second, right? Which is a very, very fast velocity. 2 kilometers per second is faster than a rifle bullet. The object will just do something like this. It will hit the ground, right? If I increase the speed to the horizontal speed of the object to something like 5 kilometers per second, it will take somewhat longer, maybe a lot longer, but it will hit the ground ultimately. What if I increase the speed to 7 kilometers per second? In that case, it's going to hit the ground almost at the other side of the Earth. So I hope it's clear to you why it's taking longer to hit the ground. I mean, it's always falling, but it's traveling sideways really fast. And so the Earth is curving underneath it, and that's why it's taking longer to get back on the ground. Okay, something magical. So this one was 2 kilometers per second. This one was 5 or 6 kilometers per second. This one is 7 kilometers per second. Something magical happens if I launch the object horizontally at a speed of 8 kilometers per second. So if you do the animation, if you do it in the simulation, this is what you will see happens. The object just never lands. It just keeps on going in a circle. And so it will just keep going in a circle forever. And it will just never hit the ground. Why? It's falling at all the time, but it's moving sideways way too fast, as a result of which the Earth is curving underneath it in exactly the same rate that it's falling. So the Earth is curving, and so the ground is going down underneath it, but it's also falling by the same amount. And so it just never hits the ground. So it's just not able to hit the ground because it's moving sideways way too fast. So we say that in this case, at 8 kilometers per second, the object will go into orbit. And this is the principle of a satellite. So a satellite stays up in space because it's moving sideways way too fast. If it were to slow down, then it would act like the trajectory. It would follow the trajectories that I showed for 7 kilometers per second or 5 kilometers per second. It would eventually hit the ground. But at 8 kilometers per second, the ground curves away underneath it at the same rate at which it's falling. And so it's just not able to hit the ground. It's trying its best to fall, but it's just moving sideways way too fast. And this is the principle of orbital motion. What would happen if I launch the object at a speed of greater than 8 kilometers per second, so maybe 9 kilometers per second? So in that case, it would go into an elliptical orbit. which would kind of probably look like this. So between 8 and 11 kilometers per second, it would go into various elliptical orbits. Right? What would happen if I launched it at more than 11.2 kilometers per second? You already know the answer. It would just fly away and not come back anymore, because 11.2 is the escape velocity for our planet, right? So you understand now what is necessary to put an orbit, put an object, put a satellite into orbit. You just need to launch that satellite. You just need to give that satellite a horizontal velocity, very, very high horizontal velocity, more than between 8 and 11 kilometers per second, and then the satellite will just go into orbit. That's all that you need to do, right? So in principle, satellites are put into orbit by putting them on a rocket, and the rocket eventually gets to that speed that the satellite needs to have, and then just releases the satellite. Now, why is it that every rocket that you've ever seen, why is it that it takes off vertically and not horizontally? So if this is the Earth, every rocket launch that you've seen, the rocket always takes off horizontally. Why does that happen? Well, the reason is that the rocket wants to go into orbit at a place which is high up. I mean, it wants to go into orbit um, several miles above the surface of the Earth, just in order to bypass the Earth's atmosphere. So going into orbit within the Earth's atmosphere would cause a lot of problems. It could crash into trees and buildings, obviously, and there is also a lot of air resistance from the atmosphere. So a rocket initially travels vertically upwards until it gets to a height where the atmospheric resistance, air resistance, is negligible, and then it turns and starts moving like this, and it speeds up to the speed necessary by firing its exhaust, and then just releases the satellite, and then the satellite just goes into orbit. There's another question. Why are rockets always launched from certain places, like Cape Canaveral in Florida, or the Baikonur Cosmodrome for Russia? So why are rockets? Why don't we have a rocket launch from downtown Nashville, for instance? The answer is that the rocket needs to have a large sideways velocity, horizontal velocity, right? Now, if you're close to the equator, the Earth is rotating like this. So let's say that the Earth is rotating around this dashed line that I just showed, right? So this is the North Pole, this is the South Pole. Okay, so what is the linear speed of a point on the equator? And how does that compare with the linear speed of a point which is not at the equator, which is somewhere at, say, 45 degrees latitude, which is approximately the latitude of Nashville? So compare the linear velocity of a point at Nashville versus the linear velocity of a point near the equator. The linear velocity, or the tangential velocity, is given by v equals r omega. So omega is the same for all points on the Earth, but where will the tangential velocity be greatest? It will be greatest when r is largest. So it's going to be greatest at the equator, because then you get the full radius of the Earth. At a place like Nashville, you don't get the full. Your distance from the axis of rotation of the Earth is smaller, so you have a higher velocity. If you're closer to the equator, your linear velocity as a result of the rotation of the Earth is the greatest. And near the equator, the linear velocity can be as high as, you can calculate this yourself, you can calculate omega for the Earth. And omega is just 2 pi divided by capital T. You know what capital T is for the Earth. It's just 24 hours. So you make that into seconds. 2 pi radians divided by that many seconds will give you the omega of the Earth. You can multiply that by the radius of the Earth, and that will give you your linear speed. And the linear speed, if you plug in the numbers, near the equator is about 1500 kilometers per hour or 417 meters per second. So that is a velocity that you just get for free, right? So why not use it? So that's why rockets are launched from as close to the equator as possible to get most of that linear velocity directly from the Earth without even doing anything. So you already get that velocity for free. Since the Earth rotates from west to east, uh, the rocket will have that particular linear velocity and it will move from west to east. All right, now there are a few more considerations here. Cape Canaveral is not exactly on the equator. Cape Canaveral is at a latitude of around 24 degrees. So that's not really near the equator. So why is it that there are places in the United States, for example, some places in the desert in California, which are much closer to the equator. So why isn't a rocket launched from somewhere in the desert in California, uh, which is closer to the equator, but instead it's launched from Cape Canaveral in Florida? The reason is the following, and you can probably figure this out yourself. The reason is the following. Uh, if the rocket is launched from California, the west coast, uh, remember that the Earth is spinning from west to east, right? So the rocket will get that same velocity from west to east. The rocket will fly from west to east. Now, what would happen if something goes wrong with the rocket? So in that case, the rocket would crash, but where would it crash? It would crash over the mainland United States, in California or Texas. And so that is why it's very risky to launch a rocket from California. If you launch the rocket from the East Coast, then if something goes wrong, it will just crash into the Atlantic Ocean. And so that's why rockets. So all of these considerations go into deciding where would be the best place to launch a rocket from. All right. Now, the next thing that we are going to calculate is the total mechanical energy of a satellite in circular orbit. So this is a very simple calculation, and I don't even need to work it out for you. You can probably do it yourself. Might as well just work through it. So we are going to calculate the total mechanical energy. You know that the total mechanical energy is just the sum of the kinetic energy and the potential energy. So we're going to calculate the total mechanical energy of a satellite in a circular orbit, right? So here is the Earth, here is the satellite. It's out at a radius r, and it's describing a circular orbit. All right. So the kinetic energy is just half mv squared. V is the orbital velocity of the satellite. And the potential energy is going to be minus gm little m divided by little r. So m is the mass of the Earth, little m is the mass of the satellite. Okay, now we already have an expression for v squared. So we've derived this earlier. So v squared is simply gm divided by r. So minus gm m divided by r, and you can just simplify this. So this would be minus gmm divided by 2r. If you just simplify it, you just factor out the gmm over r and you get half minus 1, which is negative half. So that is the total mechanical energy of a satellite. All right. So this is the total mechanical energy, the total kinetic energy, and this mechanical energy is the sum of the kinetic energy, which is gmm divided by 2r, and the potential energy, which is minus gmm divided by r, and obviously I got the kinetic energy from here. All right, so we have expressions for the total mechanical energy, the kinetic energy, and the potential energy of a satellite. So take a look at this question and see if you can come up with an answer. Looking at the formula for E in the box here, what do you think is going to happen to R if E goes up? So if E goes up, then the absolute value of this quantity will go down, right? So that means this quantity in the blue parenthesis must go down. Why? Because a negative number goes up when its absolute value goes down, right? So -2 is greater than -1000. So if E goes up, then this quantity inside the brackets will go down. And so in order for the quantity inside the brackets to go down, R must go up, right? So what we conclude is that when E goes up, the energy of the satellite goes up, the radius must go up, right? Okay, what do you think would happen to the velocity of the satellite? So the velocity is what determines the kinetic energy of the satellite. So the velocity, look at the formula for kinetic energy. If the radius is going up, as we just established, what happens to the kinetic energy? The kinetic energy will go down because the kinetic energy has the radius in its denominator. So if the radius goes up, the kinetic energy and the velocity will go down. So this is a highly counterintuitive result because you have the object over here, you have the Earth over here, and you have the satellite, and the question orbiting the Earth. The question was, if the satellite gains energy, what will it do? The answer is not what you would expect at all. You would expect something that gains energy to move faster, but actually it does not move faster. It moves to a more distant orbit, a higher orbit, I mean a larger orbit. So it will move somewhere over here, and it will slow down, right? So it's opposite of what you would naively expect. So if it gains energy, so keep this in mind, a satellite that gains energy moves to a higher radius and moves slower. What if a satellite loses energy? So if it loses energy, you can run through the same arguments and conclude that the opposite thing will happen. Its radius will go down, so which means that it would move to a closer radius. It's sometimes called a lower orbit, and its velocity will increase. So if it loses energy, its velocity will increase. If it gains energy, its velocity will go down. And if it loses energy, it moves to a closer orbit. If it gains energy, it moves to a higher orbit. Okay, so if you understand this, now I can tell you about a very fascinating application of this. Okay, so you can all recognize this planet. So this is the planet Saturn. Here you can see a magnificent picture of Saturn. Saturn has, the most striking thing about Saturn is its unbelievable system of rings. The ring system of Saturn extends from about 7,000 kilometers above the surface of Saturn to 80,000 kilometers above the surface. So if this is Saturn, the ring systems would start from, I suppose we are looking down on Saturn from above its equator, then we above the north pole of Saturn, we would see that the ring systems start from somewhere over here, and this is about 7,000 kilometers, and it extends to 80,000 kilometers. So this is almost 73,000 kilometers, or approximately a good 45,000 miles or something like that. So it's absolutely vast, the ring, the width of the ring system, and compare that with the radius of the Earth. The radius of the Earth, the diameter of the Earth is only 12,000 kilometers. So this is several times the width of the Earth, the ring system of Saturn. And what are these amazing rings made up of? They are made up of chunks of ice. So they're 99.9% water ice. So they're chunks of ice orbiting Saturn. So that's what the rings are made up of, like billions and billions of chunks of ice of various sizes orbit, orbiting Saturn. Now, we talked about the width of the ring system. It's a stunning 73,000 kilometers, something like that. What is the thickness of the ring system? The thickness of the ring system is amazingly 10 meters. So something, just imagine something 73,000 kilometers wide, but only 10 meters thick. So the ring system of Saturn is very narrow, right? So all of these particles that are orbiting Saturn, all of these chunks of ice that are orbiting Saturn are confined within a thickness of about 10 meters. Okay, now there is amazing structure in the ring system, and you can kind of see that in this diagram over here. I mean, this is actually a photographic image, though it looks like a painting. You can see this amazing structure. There are gaps in the ring system. There are various density patterns in the ring system. It's just amazing. Here you've got a big gap. The reason for these gaps are pretty amazing, but I'd be talking all day if I tried to explain them. All right, so the point is that there is a lot of amazing structure in the ring system, right? It's all because of gravity. The way gravity works is because you have all that. All right, now I just want to point out one thing. So one of the rings of Saturn is called the F ring, and you can see that the F ring has a really sharp structure. You can see that the particles in the F ring are confined to this this narrow band. So you don't have any ring particles spreading out of the F ring. So they're all confined within the F ring. Why do the particles in this particular ring stay within the ring? Like why don't they just spread out and diffuse? So what forces them to stay within the ring? So the question is the following. Here is Saturn. Okay, I'll just draw. Maybe Saturn is somewhere at the bottom. I'll just draw Saturn over here. And let's just focus on one ring of Saturn, which is the F ring. It is a band of particles that are orbiting Saturn, like this. So this is the F ring. And what I'm claiming is that all the chunks of ice that make up the F ring, for some reason, stay within this band. Why don't they drift away from the band? I mean, they're constantly colliding with one another. Why don't they just drift away from the band and spread out and diffuse? The reason is because of the existence of two moons of Saturn, which are called shepherd moons. So you have one moon over here, which is called the inner shepherd moon, and you have another moon over here, which is called the outer shepherd moon. And both of these moons are obviously also orbiting Saturn. So how do these two moons make sure that the ring particles in the F ring stay within the ring? Okay, so to understand that, we have to first think about the velocities of the particles. And let's just write down our conclusion from over here. When E goes up, the energy of a particle in orbit, when it goes up, what happens to its velocity? Its velocity goes down, and its radius goes up. I mean, the radius of orbit goes up. And if the energy of a particle goes down, its velocity goes up, and its radius goes down. So this we just concluded from the formulas for kinetic and potential energy. We are going to use this fact. All right, now consider what happens if a ring particle comes out of this ring. Everything is orbiting this way, let's say, in the counterclockwise direction. So suppose a ring particle drifts out of the ring and it gets over here. Here is our divergent ring particle. I'm drawing that as a black closed circle. Now, first of all, let's consider the relative speeds. Which do you think, let's call this 1, 2. The ring particle is 2. The particles in the ring, let's just take a particle that's inside the ring as 3, and the outer shepherd moon as 4. So I'll make shepherd moons like this. Which of these is moving fastest? The 1, 2, 3, or 4? Clearly, 1 would be moving fastest because it's closest to Saturn. Remember our formula for orbital velocity? V is equal to square root of gm divided by r. So if r is lowest, then v is going to be highest, and so the inner shepherd moon is moving the fastest. The divergent ring particle, which strayed out of the ring, is next fastest. The ring particles themselves are moving slower, and the outer shepherd moon is moving slowest, right? All right, so the particle that strayed out of the ring, which is indicated by 2, would be moving faster than all the particles inside the ring, right? However, the inner shepherd moon would be moving much faster than the ring particle. So every now and then, the inner shepherd moon would pass by particle 2, and it's the inner shepherd moon is a large moon, right? And and this particle is just tiny, it's like a pebble. So it's going to feel a force as the inner shepherd moon passes by it, right? So that tug due to the inner shepherd moon, every time it passes by ring particle 2, will give extra energy to ring particle 2. And what happens to a ring particle when it gets extra energy? If it gets extra energy, its radius goes up and its velocity goes down. So eventually, as it keeps getting more and more extra energy, it will go back into the ring. The same exact thing happens if a particle gets out of the ring on the other side. So suppose a particle, let's call that 5, gets out of the ring on the outer part of the ring, right? So now 5 would be moving faster than the ring particles, slower than the ring particles because it's got a larger radius, but faster than outer shepherd moon, which is number 4, right? So what's going to happen is that when 5 passes by the outer shepherd moon, every time it passes by the outer shepherd moon, it's going to feel a tug from the outer shepherd moon, which is going to pull it backwards because the outer shepherd moon is moving slower than it, right? So as it passes by it, it's going to feel a pull to the, it's going to feel a backward pull. And so that's going to take away energy from it because it's like a drag force. It's going to take away energy from it. And so as it loses energy, what happens to a particle in orbit as it loses energy? It speeds up and moves to a lower orbit. And so this will also eventually move back into the ring. And so any particle which diverges from the ring eventually gets back into the ring as a result of these two shepherd moons. And this is absolutely amazing. The presence of the shepherd moons was first postulated by scientists because they were amazed by how sharp this ring looked. So it looked like there must be some influence on the ring which maintains its sharpness. And so they suggested that it's probably shepherd moons. And then these shepherd moons were actually seen and photographed. Okay. And yeah, so here's a picture of one of the shepherd moons. Okay, so that was just an application of the relationship between the total mechanical energy and the velocity and radial distance of an object in orbit. And that concludes our discussion of gravity. I must briefly mention here that Newton's law of gravity is not the full picture of gravitation. Einstein realized in the early part of 1900s, between 1910 and 1920, that there is something wrong with the way we view the gravitational force. And he realized that gravity is not really a force at all, but a manifestation of the warping of space and time. And so gravity is not really a force, it's a fact that if an object is sitting in warped space-time, um, the way it's going to behave is what we interpret as a gravitational force. And so that idea is called the general theory of relativity. And that's obviously way beyond the scope of this course. But I just wanted to briefly mention it before concluding this video.